Hello students. In this lecture we will be studying about uh, ferrofluids. Now these are also called magnetofluids. So it's magnetism in fluid state. Now magnetofluids they show magnetism because they have colloids or the magnetic particles in the form of colloids of size 10 nanometer on an average. So that's how this fluid gets magnetic. And apart from these colloids, these ferrofluids also consist of surfactants. In fact, the surfactants are acting as a coating on the colloids to prevent aggregation. So these magnetic fluids and magnetic particles are again coated with surfactants to prevent aggregation. Now, a surfactant, you know that there is a hydrophobic and there is hydrophilic group. So if the particles are covered with surfactants, so naturally two hydrophilic or hydrophobic groups come in contact with each other will cause repulsion between the magnetic particles. So hence they will prevent aggregation. Now, when we talk about nanoparticles, so when we talk about magnetic nanoparticles, for that instance, so these are the size since it becomes so small. So one nanoparticle will have one domain. So we can call it a single domain magnets. And the magnetic field or the magnetization vector of each of the particles are randomly oriented. The magnetization of each particle are randomly oriented. So hence the net magnetization is zero. Gives a zero net magnetization. Now, when an magnetic field is applied into these magnetofluids, the magnetization starts to take place. So if we plot magnetization M in terms of mu per gram with respect to magnetization field or H invested, then we will get a plot like this. 10 Oersted is equal to 10 to the power minus 4 Tesla. So this behavior, this is a non-hysteresis behavior, and it's a behavior of a soft magnet. So we obtain soft non-hysteresis behavior of the ferrofluid. And since the particles are in nanometric range, so there is a chance that this property is actually some super paramagnetism. Now, the difference between a super paramagnetism and a magnetism, how will you differentiate? You can differentiate by the magnetization vector, the saturation magnetization. So, although they look the same in an image plot, although both of them are S-shaped, however, the saturation magnetization of a supermagnetic is much higher compared to a paramagnetic. So this is super paramagnetic material, and compared to that, if you plot a paramagnetic material, it will be very small. Maybe like this. So this MS value is what differentiates a supermagnetic material from a paramagnetic material. So since here the magnetization or the saturation magnetization value is much higher, so we can assume that, we can say that in ferrofluids, super paramagnetism takes place. Now, if again the field applied, the magnetic field applied is a DC magnetic field applied, so the fluid is in terms of solid mass. So this is magnetic field dependent and isotropic property observed in ferrofluids. Magnetic field dependent and isotropic behavior observed in ferrofluids. And this property is analogous to what is observed in liquid crystals. So we can say that analogous to liquid crystals, LC. And in liquid crystals, what happens is that long molecular large electric dipole moments oriented by electric field in the fluid phase. So when we apply electric field, so there is a long molecular alignment, and due to that there is a long molecular change or alignment, I should say, and then there is a large electric dipole moments. So Similar to this in ferrofluids, when we are applying an electric and magnetic field, so applied in ferrofluid, so some particles are lowered and a needle-like chain structure is formed. Like chains are formed. So let's do something with this. H applied, and so this is 30 micrometers width. So we'll see agglomeration of magnetic fluid particles takes place. Now, as we increase the magnetic field, this is increased. So more and more particles join and the chains becomes longer in border. So more particles join and the chain becomes longer and broader. And however, the separation between the chains, they are reduced. Chain separation, it gets reduced. So you can say that if we express chain separation in terms of micrometers, and we plotted with respect to the applied electric field, magnetic field, so we can see a sharp fall of the value like this. However, the chain width, on the other hand, doesn't show a monotonic decrease. Chain width expressed in micrometer, plotted again with magnetic field, so it takes the path like this, zigzag path, not a monotonic decrease. So ferrofluids can be used as a diffraction grating. Due to this property of alignment and forms of chain, they can be used as diffraction grating. We can tune the magnetic field to avail this property, and the path length, if we have used this ferrofluid as a grating, then the path length will be equal to n into lambda by 2 for the dark lines, or the multiple of lambda, and integral multiple of lambda for bright lines. So this is for destructive interference, called D, and this is for constructive interference, C, path length. Now, what happens when we are applying the magnetic field in perpendicular direction? We are applying it in the parallel direction. So if you apply it in perpendicular direction, then two-dimensional hexagonal lattice is formed. 2D hexagonal lattice is formed, and the columns of nanoparticles occupying the lattice sides. So it acts as a 2D optical diffraction grating. And the diffraction from this optical diffraction grating, it produces circular chromatic rings. Now, if you do analysis of the diffraction pattern, then that is d sin theta is equal to n lambda, where d is the separation between the chains, and theta is the direction angle between the outgoing light and normal. Now this separation, as we have seen, this separation between the chains, this d is a function of the applied electric field. So what we're getting a tunable diffraction grating. You can tune tunable diffraction grating. So with the help of the magnetic field, we can change the slit width of the diffraction grating. Now, applications of ferrofluids. Ferrofluids are used in as seals in hard disk drives. And also they act as vacuum seals. Now, the formation of chains that are formed in the ferrofluids, these chains in ferrofluids, these chains actually make them optically anisotropic. Anisotropic, and it acts as a polarizer also. So if we have a light which is linearly polarized, so we allow it to pass through a ferrofluid with magnetic field applied, and then it becomes elliptically polarized. Linearly polarized means vibration is confined to one plane of perpendicular to the direction of propagation. Elliptically means elliptical direction. Now, in elliptical, so let's understand what is a linear polarization. Linear linear polarization, the vibrations are confined in the one plane perpendicular to the direction of propagations. Confined in plane perpendicular to the direction of propagation. So this is the direction of propagation. There will be a plane here. All the vibrations will take place, and this is the linearly polarized. This indicates it is linearly polarized. Whereas elliptical polarization, in elliptical polarization, the electric and magnetic fields, they are confined to two mutually perpendicular planes, two mutually perpendicular planes. And another phenomenon is the vibration in each plane is out of phase. And this phenomena of vibrations being out of phase in each plane, this is called photon-moton effect. So if we draw the diagram, it will be like this. The source is a helium neon laser. It falls on a polarizer. From there it moves to the sample. Then it moves to the analyzer. And then to the detector. So this axis is the t-axis, the transmission axis. And the angle with which it comes out of the analyzer is this angle. So this angle is called the azimuthal angle. And eta. And if we plot azimuthal angle with respect to intensity, right intensity right I with respect to azimuthal angle, we see that, say, from 93 degrees to 87 degrees, we see a plot like this. So at around 90 degree you get a downward fall, and this is for when the bright field is equal to 0, And when we are increasing the field, there is a rise in the intensity. So this is say H is equal to 200 Oersted, and the value is 0.002 relative to the initial intensity. So we can conclude that the transmitted light intensity depends upon the azimuthal angle. And this forms the basis of optical switch, where we can switch on and off by using a magnetic field.